Welcome back, ladies and gentlemen. In this video, we're looking at this thing called relative motion. And essentially, it's a way to find the motion of one object relative to another object if both are moving, but maybe they're both moving relative to yet a third object. And so the example is a classic example of a boat trying to cross a river. Typically in a river, you got water moving in one direction, and there's going to be this boat trying to get across the river. So there's my boat, and we're just kind of aiming the boat straight across the river, and we're going to see what happens. Well, you have some intuition about what's going to happen already, I'm sure. You have this idea, well, look, it's not going to get straight across because the water's pushing it sideways. There's going to be the addition of vectors here. The water's velocity this way is a vector. The boat's velocity this way is a vector. And there's going to be a resultant when we combine those two. Let's identify a few things, though. We have velocity of the boat relative to the water. So here's our notation, velocity of the boat relative to water. And let's give that 1.2 meters per second. And we have velocity of the water relative to the ground. And let's give that 3.1 meters per second. So what we're saying is, with this notation, the velocity of something relative to something else. And you can see that we've got boat and water and ground, but we don't have relative velocity of the boat compared to the ground. So that's going to be what we're going to find. What is the velocity of the boat relative to the ground? So velocity of the boat relative to the ground is the unknown here. Now, I'm sure you can kind of see this already. What we think is going to happen is the boat is not going to go straight across. The boat is going to go something, I don't know, some direction like that. That's going to be our resultant, or the velocity of the boat relative to the ground. And let me label the other two real quick. Velocity of the boat relative to the water. And this guy, oh, where'd that wonderful green go? I'll use this green. This is the velocity of the water relative to the ground. Okay. So what do we see here? We can see this kind of triangular shape taking place. The vector's happening. So we have this velocity of the water relative to the ground. We have this velocity of the boat relative to the water. I got my symbol in the way, didn't I? So that guy right there would be the velocity of the boat relative to the ground. That's the guy we're looking for. We have a right triangle. This is going to be pretty easy. Setting this up, well, we're adding vectors here, but we can say, look, the hypotenuse, velocity of the boat relative to the ground. Since it's a right triangle, hypotenuse is equal to the square root of the sum of the squares of the sides. Velocity of the water relative to the ground squared plus velocity of the boat relative to the water squared. Pythagorean theorem. And so put some numbers into this, and velocity of water relative to the ground is 3.1 meters per second. We're going to square that guy. And velocity of boat relative to the water, 1.2 meters per second. We're going to square that guy, and this whole thing is under the radical. Calculator time. Velocity of the boat relative to the ground is 3.3 meters per second. Wonderful. That's how fast it's going relative to the ground. But we are missing something. And the thing we're missing is pretty important right here. What's that angle? What's that direction? Well, not so hard to find. Let's take a look at that. I can't use that color. Let's go. Here we go. With that angle, the angle here in our right triangle, by the way, since we have so much information, we have some choices we can make. I'm going to use tangent. I know that tangent of an angle is equal to opposite over hypotenuse. Now I'm picking opposite and hypotenuse. Oh, shoot. Erase. Hypotenuse. What am I saying? Opposite over adjacent. Ay caramba. So, and so I'm picking those two mostly because they're given to me, and those aren't numbers I've calculated. So maybe they're more trustworthy. I don't know, but I'm looking for angle theta. So inverse tangent of, and so the opposite is velocity of the boat relative to the water. Adjacent is velocity of the water relative to the ground. And there's how I find the angle. This is only one way to do it. I've got my inverse tangent of 1.2 divided by 3.1. Come on, paper. And so I get the angle here, 21.2 degrees. So I kind of have two parts to my answer. The final answer, velocity of the boat relative to the ground, is right here, 3.3 meters per second at an angle of 20. I call it 21 degrees. I've only got two sig figs everywhere else. 21 degrees. Well, okay, that's 21 degrees sort of east of north, right? Or 21 degrees measured from the positive y-axis in this sort of point of view. But that is it. I've got the speed, I've got the direction very clearly done. Boom! It's good. Now, let's generalize this and then apply it. So we can continue. Generally, oh my goodness, paper. We're going to say, well, what we did was the velocity of something is equal to the sum, the vector sum of the velocities of two other things. So let me put this down here. So we have the velocity of one thing compared to something else. Now notice I didn't use number 2. Velocity of object 1 compared to object 3 is equal to the vector sum of the velocity of object 1 compared to object 2 plus the velocity of object 2 relative to object 3. See how that works? And so we have to be thinking in terms of vectors here. That totally matters. I can't just do sort of a arithmetic sum here. You know that doesn't work because direction is also wrapped up in all of this. So let's apply this. I've got a question. Let's work on this particular question. Check it out. If that boat traveled at 4.5 meters per second relative to the water and the water flowed at 2.1 meters per second relative to the ground, then in what direction would the boat have to be pointed in order to travel straight across the river? So the numbers are different, but you can see this is also a different question. Our goal is to get the boat straight across. So how do we tackle this? First, a sketch, right? Here's our river. Go a little larger. Got the water flowing this way, and we've got a boat, and we're hoping that we're gonna try to aim the boat so that it ends up going straight across the river, right? But what that means is this vector here is not the velocity of the boat relative to the water. That's the velocity of the boat relative to the ground. That's our goal there. And we also have a velocity of the water relative to the ground coming in like this. Velocity of the water relative to the ground. And what we're going to have is this thing there. And that is the velocity of the boat relative to the water that it needs to achieve. And you can see an angle here that's necessary to achieve that. So let's figure this out. Here we go. Let me identify some values here. Velocity of the water relative to the ground is our 2.1 meters per second. Velocity of the boat relative to the water is, we know that value, that's the 4.5 meters per second. And really, it's the angle theta here that is the answer we need. So let's go about doing that. I sure have a right triangle all over again. I mean, you can easily see that right here. But let's see. I know a couple sides of the right triangle, and I'm looking for an angle, so this is pretty easy. Sine of the angle is equal to opposite, which I know, divided by hypotenuse, which I know. And the opposite is my velocity of the water to the ground. My hypotenuse is my velocity of the boat relative to the water. But I'm looking for the angle, so I'm going to inverse sine this whole thing. And therefore I get theta is equal to inverse sine of that business, and that business is, I've got my 2.1 and my 4.5. So it's not too hard to figure this out. The answer I get, 27.8 degrees. Oh, when you're doing this, you calculus people, you want to make sure that your calculator is in degrees mode, not radians. There will come a point in this course when that will be different, and you'll actually use radians mode just because it's more convenient for us. But for some time now, you want to be thinking, well, are we using degrees? Then I need to make that adjustment on the calculator. Well, that is the angle the boat must achieve. Maybe I should specify sort of west of north, like that. West of north. Now, that was pretty easy, yeah? I could answer one more question about this pretty easily also. What about the boat's velocity relative to the ground? What about that guy right there? Can I find that? Well, yeah, no problem. I have my right triangle, and I have plenty of information about it, and this is just the side that's adjacent to the angle. So that's going to use cosine. Cosine of the angle is adjacent divided by hypotenuse. So inverse cosine. And the adjacent is going to be, oh, what am I doing? Oh, I'm not looking for the angle. Holy cow. I'm looking for the adjacent side. Goodness. The adjacent side is going to be the velocity of the boat relative to the ground. And so I'm going to bring this over to this side. So I have hypotenuse, which is my velocity of the boat relative to the water, times the cosine of the angle. And I know the angle, so I'm good to go. What is this velocity of the boat relative to the ground? That's going to be, let's see, boat to water is my 4.5 meters per second times the cosine of 27.8 degrees. Squeeze it right in there. Paper, velocity of the boat relative to the ground, and I do that math. 3.98 meters per second. Okay, so we are definitely using this style of relationship. We are doing vector addition to solve problems like this. All right, that's it for now. Thanks for watching. I'll catch you next time.